A 100-ton aircraft, visible to our naked eye, can travel 10,000 kilometers without being detected by any conventional radar. Yes, we're talking about the B-2 stealth bombers, each costing $2.2 billion. Just as the B-2 was becoming a legend, on June 18th, China announced that it had developed a quantum radar, implying it could detect the B-2 on radar. The fundamental question is this: why do these weapons require so many physicists? So, if you're ready, today, we're examining military technologies through the number of physics PhDs in different countries. Again, our core question: why do these weapons need so many physicists? On a hot June night, at the foot of a desolate mountain illuminated by a full moon, in a secret base built exactly 90 meters below ground, you are in charge of the radar. Your eyes are fixed on the screen, scanning for silently approaching threats. Outside, a group of elderly men glorifying themselves with moral superiority narratives are directing armies equipped with stealth aircraft. These planes can fly 10,000 kilometers without refueling and carry up to 26 tons of bombs, including nuclear ones. Their single objective: your base. Your advanced defense systems capable of instantly neutralizing incoming aircraft are all tied to a single button. But there's one problem: these planes are invisible to radar. Let's say they arrive and drop their bombs without leaving a trace. Your only consolation is this: you're in a deep bunker 90 meters underground, surrounded by granite rock. That means it's not enough for the enemy's bomb to simply reach the inside of the bunker. It must penetrate 90 meters of granite to reach the core of the facility, and it must do this before the warhead detonates, at the exact moment of impact. While that may sound impossible at first glance, the claim is that, unfortunately, it is entirely possible. So how can this futuristic-sounding scenario actually happen? The Americans launched the Stealth Aircraft Project in 1970, followed by its first test flight in 1989. And this aircraft ends up striking nuclear facilities in Iran in 2025. It's clearly a strategic move. And let's not forget that the same strategic, or perhaps tragic, mindset also spread nuclear weapons technology around the world. The main contractor behind the stealth aircraft is the American company Northrop Grumman. At least 20 other subcontractors are also involved in the project. The main contractor employs 100,000 people and continually recruits PhD-level mathematicians and physicists. This company is especially known for offering high salaries to physicists. If you're wondering what they need these physicists for, here's the answer. Right now, the chart you see on screen shows the number of physics PhDs awarded by country in recent years. We've compiled this data from open sources, and we believe the results reflect reality to a large extent. If you look closely at the table, you'll start to understand how this whole system works. The Americans have consistently awarded around 1,800 physics PhDs every year without interruption. There's no magic here and no alien intervention either. What we see is the direct use of science in weapons technology. That's the whole story. Some may ask, what does the number of PhDs have to do with this? Let's clarify. Weapons development is one of the negative externalities of science. In principle, scientific research is not carried out with the intention of creating weapons, or at least, it shouldn't be. However, we've reached a point where science is increasingly falling under the influence of the doctrine of mutual deterrence. This doctrine is based on the belief that peace is ensured by opposing forces having equal destructive capabilities. As a result, even if that's not their intended purpose, scientific efforts end up contributing to the arms race. Modern weapon systems, especially nuclear weapons, ballistic missiles, directed energy weapons, and quantum-based technologies, operate on complex principles of physics, and developing these systems requires experts with advanced knowledge in both theoretical and applied physics. Therefore, the number of physics PhDs in a country is not only a measure of academic productivity, but also a rough indicator of that country's capacity to develop and integrate advanced weapons technologies. Without scientific manpower, laboratory infrastructure, and a long-term research culture, producing high-tech weapons systems is nearly impossible. Traditional radars emit electromagnetic waves and wait for those waves to bounce back from objects. However, stealth aircraft like the B-2 possess special designs that absorb or scatter these signals, resulting in extremely weak or even non-existent returns. This makes them invisible to conventional radar systems. The core of this technology lies in a concept called radar cross-section. The lower an object's RCS value, The less radar signal it reflects, and the smaller it appears on radar. Aircraft like the B-2 minimize their RCS by using specific geometric shapes and radar-absorbing materials. For example, angled surfaces scatter radar waves in multiple directions, while RAM converts incoming signals into heat, preventing reflection. It might sound easy, someone might say, let's build one ourselves then, but it doesn't work that way. With so many engineers around the world, one may wonder why only the Americans have been able to do this. In fact, the Americans aren't alone. Russia's Su-57 and China's J-20 have made significant progress in stealth technology, though their radar signatures aren't as low as the B-2s. The J-20, in particular, stands out as China's fifth-generation fighter jet, using radar-absorbing coatings and aerodynamic designs. Even so, the B-2's nuclear payload and range remain unmatched. But are consistent PhD numbers really enough for stealth aircraft? Well, the cost of invisibility is steep. The B-2's radar-absorbing coating is as delicate as a butterfly's wing. Rain, ice, or even dust can degrade its performance. After each flight, it requires hours of special maintenance and invisibility restoration. This pushes the operational cost to $130,000 per flight hour, with each sortie costing up to $10 million. Stealth isn't just physics, it's an endless logistics operation. So, how is it that some succeed in this field while others fail? Scientific studies on the absorption and scattering of radar waves form the foundation of stealth aircraft technology. If you lack qualified researchers in this area, your project may never even get off the ground. Accessing such papers through open sources isn't always easy, but we gave it a shot, and let's review who has done what recently. The first article is titled Laser-Fabricated Graphene-Based Cloaking Materials. All three authors are Chinese, affiliated with Chinese universities. The paper proposes a material potentially suitable for stealth aircraft. Moving to the second study, we find a simulation model of the electromagnetic behavior of aircraft coated with radar-absorbing material. Again, from China. The third paper investigates, numerically, how morphing circulation-controlled wing surfaces reflect radar waves. This, too, is a Chinese study. At this point, it's worth pausing to reflect. The fact that our Google search yielded 3 Chinese articles may be due to the algorithm, or it may simply be coincidence. But when a country produces 3,000 physics PhDs per year, the density of research in this field is hardly surprising. Given all this, it comes as no shock that China's stealth bomber, the Xian H-20, is currently in the prototype phase. If we see it in the skies soon, we won't be surprised. Now, let's say you build a stealth bomber, but how do you protect yourself from enemy stealth aircraft? This is where the quantum revolution steps in. The entire design of the B-2 stealth bomber represents the pinnacle of classical physics principles. But no matter how advanced, it's still bound by the limits of classical physics. And every time I hear someone say, from this point on, quantum takes over, it always seems to follow a boundary like this. The limits of the B-2 are drawn by quantum radars. Radar technologies detect and track objects using the reflection of electromagnetic waves, but these systems have always had certain limits. Traditional radars operate with limited resolution based on the object's size, shape, and surface material, and they struggle especially with low radar cross-section objects. Even though radar systems based on classical physics have been developed to overcome these limitations, stealth aircraft designed with electromagnetic scattering-resistant materials or geometries can still deceive these systems. This is where quantum radars come into play. They use the principle of quantum entanglement between photons and don't rely solely on reflection like classical radars do. Instead, they also analyze wave-particle interactions and quantum correlations. Classical radars rely on the return of emitted signals. However, B-2 stealth aircraft absorb or deflect these signals, making them difficult to detect. Quantum radar, on the other hand, uses entangled photon pairs, one sent toward the target, the other kept in the system. If the sent photon strikes the B-2, it may not reflect back, but it will undergo a change in properties, such as polarization or phase. This change can be detected by comparing it with its partner photon still in the system. For example, a photon that was initially horizontally polarized might return as vertically or elliptically polarized after hitting the aircraft surface. This mismatch reveals that the photon interacted with something, indicating the presence of the B-2. Thus, quantum radar can reveal stealth objects that traditional radars miss, using subtle traces at the photon level. And yes, on June 18th, 2025, believe it or not, China announced it had completed its first programmable quantum radar. They declared that stealth aircraft are no longer a threat. This news was spotted on sites like and several Chinese media outlets. While conclusive proof remains absent, it is well known that China has been investing heavily in this field. Such a system must be mounted on a high-altitude airship or UAV. Allegedly, this radar could detect not only the presence of stealth aircraft, but also detailed information about anything within its range. Naturally, creating such a system requires a great deal of scientific research, and China is truly investing in it. But this magic is not yet perfect. Entangled photon pairs can easily lose their quantum correlation over distances greater than 50 kilometers due to atmospheric conditions such as humidity, temperature, and turbulence. China claims to have developed a programmable system that surpasses this range limitation. However, Western experts argue that operational quantum radars are at least 10 years away from becoming a reality. This is why China's claim still requires verification. Meanwhile, China is catching up to the Americans, who have maintained consistency in producing physics PhDs for decades. Those who refuse to train PhDs in physics and mathematics, or fail to pave the way for such development, must get used to living under the threat of invisible aircraft. If you don't have science, you don't have the chance to exist. Until we meet again in more hopeful videos.